In this video, I will explain how we can derive the speed of sound using partial derivatives that we have covered so far. The speed of sound is something that you probably have known since high school, or at least in first year physics, and there are a number of important applications for it. For example, from the sound of the thunder, and from the time that you have seen the lightning, you can calculate the speed of sound in air. Sonar is an important device that's often used to detect objects that are underwater or invisible to the naked eyes. But in the old days as well, in athletics, the guy who was keeping the time during competitions, they used to use the speed of sound. Obviously, these days, they have all sorts of electronic monitors and so forth. But the idea here is that the guy over here is going to start his competition, and there is a guy with a gun in here. And when the guy fires the gun, the sound will be heard by this guy over here. This is the timekeeper, and then he will click it. So if you actually lose some time by, which will be the time that the sound takes to travel from the guy who fired it to the guy who is keeping the time, you can see that the athlete is going to be at a disadvantage because he will be losing some time or gaining some time depending on how you look at it. So the equation that we really are interested in deriving here is C, which is the speed of sound, is given by this expression here. And I don't want you to get confused with the letter C and the speed of light. We are talking about speed of sound here, and so C is just the speed of sound. So I'm just going to go directly into the derivation, but you can see that it is V sub B, which is the specific volume of the fluid, multiplied by the square root of this partial derivative at constant entropy. And that's what I'm going to do now. Just perhaps before I go into the derivation, we need to know what a sound wave is. A sound wave is a mechanical wave. It is not an electromagnetic wave. And because sound wave is a mechanical wave, it requires a medium for it to travel. And the mechanism by which sound waves travel is by means of molecular interaction, which is caused by compression of particles as a result of pressure disturbance. And so if the pressure, the particles are disturbed at one point, then they will push the next particle and they will transmit the energy into the next particle. Then that in turn will transmit the energy into the next particle, and it basically goes on and on, and that's how it propagates. So you may have seen this one in high school, but if you haven't, it's really a cool experiment. And it just illustrates that sound cannot travel in a vacuum. So what I want you to do is just perhaps go into this link and watch it yourself. This is an electric bell, as you can see it here. And what you do is you supply the power, obviously, and then when you push the button, the electric bell will start ringing and you could hear it. But what happens if you actually attach a vacuum pump at the bottom in here and suck the air out of this jar? Obviously, as you suck more and more air, then the sound is getting lesser and lesser and lesser, and at some point you will not actually hear the bell sound. You can see it vibrating because the jar is a transparent jar, but certainly you cannot hear the sound that is coming out. And so that's just a simple demonstration that, in fact, sound is a mechanical wave and it requires medium to travel because it cannot travel in a vacuum. The other interesting thing that you probably may have seen it is is what is called sonic boom. And this is a situation where if you have an aircraft here, a fighter jet or something of that nature, it is actually traveling at a particular speed. And when it travels at a particular speed, it pushes the air around the aircraft. And so that pushing effect causes pressure wave that travels at the speed of sound. But what happens if the object is actually flying at the speed of sound or higher? In that case, what you get is that the pressure disturbance is not fast enough to actually go rapidly from the aircraft body, but rather what you see is this shock wave created because the fluid cannot actually travel fast enough compared to the object. And again, you can go and you can look at it yourself. It's another cool picture, and hopefully you will understand that. Our goal here is actually to derive the equation. Okay, how do we derive it? Consider that we have a tube with cross-sectional area, and it's filled with air, for example. And for simplicity of the derivation, we have now a piston attached to one end of this tube, and the fluid inside this tube is characterized by the pressure, the temperature, and VB. Here V sub B is the specific volume of the fluid. Now it's very important that you make this distinction. The unit of a specific volume is cubic meter per kilogram, and we need that. Just keep an eye on that. So initially we have a pressure on the side, and the fluid is in its undisturbed state, and so you can see it that it's uniformly shaded in here. But what happens when you actually apply a differential amount of pressure to that fluid by pushing the piston? So you exert a pressure, and so what you do is you're compressing this fluid. And so the speed at which you are pushing this piston here is, let's say that's u. That is the velocity in which, or at which you are actually pushing the piston. When you do that, there will be a compression wave that's generated, and you can see that the compression actually generated a darker region in this area here. And so if you look at then this region, you can see that the air around in here is undisturbed, but the air around in here has been compressed. So then the distance that this compression causes is just simply given by the time times c, which is the speed of the compression wave, which is, of course, the speed of sound. Okay, so the mass of the compressed fluid then in this region here is simply given by the total volume of the fluid inside this tube or this cylinder divided by the specific volume of the fluid. And the total volume is just simply the area times the speed of the wave times time divided by specific volume. So that is just the mass of the fluid, and if you actually do a unit analysis, it would actually give you exactly the unit of mass. Then the change in the specific volume as a result of the compression process is just simply delta V over M. And this delta V over here again is the change in the specific volume. This is supposed to be a V sub B there as well. So you have here the change in volume divided by mass. And remember that this is actually going to be negative because it's compression. So when you compress the fluid, of course, the change in volume is going to be a negative quantity because, obviously it's compression. So here you have then the area times the speed at which you are pushing the piston times the time divided by the mass of the fluid. But the mass of the fluid, as I showed you over here, is just simply given by area times the speed of sound times t over the specific volume of the fluid. So you can simplify this and you'll get this expression. And in terms of derivative, and instead of the finite difference in here, if you just put it the derivative notation, here we have dVb equals minus VBU over C. Okay, now that's just a change in volume. And then we are looking at the rate of momentum change. The rate of momentum change is simply the time derivative of mass times velocity, which is u. But the rate of momentum here is just simply force. The rate of momentum change is just simply force, which is dmu by dt is force, and force equals area times pressure. The area in our case is obviously a constant area, and times the differential pressure of the system here, which is over here. So the force is just simply area times pressure, except that the pressure is in a differential notation. Then we separate this equation and we are going to integrate it. So you take the dt into the other side, and so what you'll have here is just separation of variables. This is a very simple thing. And here you have a dp dt, which is integrated between t1 0 to t2 any time of interest, and equals the integral of dmu. And if you do this integration and you rearrange it, you will get dp, which is mass times velocity, is given by this expression here. Okay, so that's very useful. And then over here we have the differential specific volume change. Over here we have the differential pressure change. And so we are going to take the ratio of dp with respect to dVb. And so what I have done here is this is dp, which is given by the expression that we derived above, and this is dVb, which is the expression again that we have derived up in here. So when you put these two together, then you have this derivative, dp by dVb equals minus c squared over vb squared, where c is the speed of sound. Now obviously I did not talk about the constant that is shown up in here, which is entropy. So you may be wondering where the entropy actually comes in this equation. And for that, a little bit of history is useful. The first person to have attempted to derive this equation was in fact Newton. So Newton taught that the compression wave that was propagated through this process as a result of pressure and volume change was an isothermal process. So which means something that was taking place at constant temperature. But experiment didn't actually support the notion that sound propagation was an isothermal process. But it turned out that the sound wave causes some oscillations in the pressure, but the oscillations are fast enough that heat cannot be transferred from the compressed region to the uncompressed region in order to keep the temperature constant. So if you actually look at how heat transfer is taking place, we either need a larger area or we need a long time. And because the wave is moving so fast that there's really no time for sufficient heat transfer to take place so that the temperature will be constant. In fact, before the heat can be conducted away from the compressed regions, the compression wave has already moved on. And that means that there's no heat transfer. And if there's no heat transfer, then the process has to be adiabatic. And adiabatic processes are characterized by a constant entropy, and so hence we will put the entropy to be constant down here. So this is now the speed of sound equation that we'll be utilizing. So if I just simplify this and write it, what you see in here is C is just simply given by VB into the square root of this term as shown. And that's just really rearranging this equation and solving for C. And you can see that this is VB square, and I took the square root of it, and then it's VB, and that's why it's actually outside of the square root, and everything else is the same. Now this equation, as you can see, is pretty much useless because we cannot really do very much with it, given that the entropy is the one that is kept constant. So as usual, what we try to do is we try to get rid of this entropy and see if we can express it in terms of measurable quantities. And that's what I'm going to show it to you next. This particular slide is in your notes, and so I suggest that you go and you practice, and you practice, and you practice until you really understands it. So from the previous slide, the speed of sound C is given by the specific volume of the fluid multiplied by the square root of this partial derivative, and remember this is a negative, while the entropy is kept constant. And so the specific volume is something that is easy to measure for any fluid. However, this partial derivative is very difficult to measure. So we are going to convert this partial derivative that we cannot measure into something that we can. And here is how you do it. And just before I go in, I show you these steps, I just want you to pay attention that for the purpose of writing it cleanly, I replaced VB by V. So the volume terms that you see in these partial derivatives in here are actually VB, except that I on purpose ignored the sub B there so that it doesn't clutter the slide here. So the answer that we will end up having is obviously this one, but what I will be showing it to you is the step. So we start from this expression here, and that is down here. That is our expression there. So you apply a chain rule, and so you can see that this is split into two, and remember that in a chain rule, the variable that you're keeping constant are exactly the same, so they both are entropy. And if you actually do that and you cancel this one, you get dP by dV at constant S, which is exactly the same thing. And then what we'll do is we'll apply the cyclic rule to each of these two expressions over here. The cyclic rule, or the triple product rule, is the one that I discussed with you on Friday during the tutorial. And so this one will give us the partial of S with respect to volume at constant temperature times the partial of T with respect to entropy at constant volume, and you put a negative sign. That's the rule. And then you do exactly the same for this other one. Now you may be asking me, why do we need to do that? Well, the reason is that this expression has Cp and Cv, and then therefore I have to get heat capacity at constant pressure and heat capacity at constant volume from these two expressions. But I know that this is, in fact, T over Cv. If you look at the definition of Cv, you can see that that's T over Cv. This is Cp over T. And so when you apply the cyclic rule and then use the definition of Cp and Cv, you actually simplify it. So you can see that it is already looking something that we are actually after. And so then you rearrange it, and the two negative signs will cancel out, the temperature will cancel out this temperature, and so it becomes Cp over Cv, and that is what you have, times these two partial derivatives. And then again, if you actually look at it, you can apply now the chain rule to collapse this thing into a single derivative. because the temperature is constant here, the temperature is constant in here. I say entropy, entropy, so they cancel out. And so what you get is really just dP by dV, which is the partial of P with respect to the partial of V at constant temperature. And so you end up having this. And so when you combine this thing, what you get is this whole term is just simply what you get in here. So this is actually just a repeat. I just repeated it twice. But in fact, this is exactly the same expression. What do we do with this equation? All right. Well, now it's useful. So let me just demonstrate to you with a couple of examples. And again, the TA or myself, when I'm back next week, I will be able to solve as many problems as possible so you can feel very comfortable. So for a fluid described by the ideal gas equation of state, let's evaluate this term. This is now the speed of sound equation. So here is the expression, and we want to know what is this value here. That's what we are after. Well, the equation of state for an ideal gas is P equals RT over V. But remember, in the ideal gas equation of state, V is the molar volume. But in the equation for the speed of sound, what we have is the specific volume. So what we need to do is find a relationship between the molar volume and the specific volume, and that can be related easily through the molecular weight. So the molar volume is the specific volume, which has got units of units of volume per mass, and molecular weight, which has got units of mass per mole. And you can see that the units of mass will cancel out, giving you molar volume, which is cubic meter per mole. And so every time I see now VB over here and VB over there, I replace that. And so first, let's take the partial derivative in here. This is just simply the same as in the partial of P with respect to the partial of the specific volume, but the specific volume now is V over molecular weight from this upper expression there, and you plug it, and because molecular weight is constant, you can pull it out and it becomes up in here, and now you have dP by dV at constant temperature. Now this V is molar volume. It's not specific volume anymore because I simplified it. Here you have minus molecular weight RT over V square. When you take the partial of P with respect to volume at constant temperature using the ideal gas equation of state, you can see that this becomes minus RT over V square. So that's what we have in here. So then we take this equation up in here and we write it again. And in this step, what we do is we eliminated the specific volume VB in favor of V over molecular weight. And here we have Cp minus Cv, which is, what we have derived earlier. And here we have molecular weight, RT over V square, and it's negative. And so the two negatives will cancel out, so it becomes positive. And then if you take the molecular weight inside the square root, and then you make it squared, and you take V inside the square root, and you make it V square, then you can see that the V square cancels this V square. The molecular weight square cancels one of the molecular weight, and you end up having RT over molecular weight under the square root. So this is the speed of sound for any fluid that is described by the ideal gas equation of state. Well, the interesting thing about this equation is that the speed of sound for an ideal gas is actually independent of pressure. It doesn't matter what the pressure is. It actually depends only on temperature and obviously molecular weight. Because this, for an ideal gas, Cp is 7 over 2R, Cv is 5 over 2R, so the ratio of Cp over Cv is 1.4 times R, and R is the universal gas constant. And R is again a constant, and T is the temperature, so the molecular weight and the temperature are the two variables. If you're considering the speed of sound at constant temperature in different fluids, then obviously the molecular weight becomes very, very important. So you can see that, for example, sound travels much faster in hydrogen than it would in oxygen because the molecular weight of hydrogen is very small compared to oxygen, and that small number is in the denominator, so making C to be a very large number. For liquids, we know that dP by dV at constant temperature is minus 1 over kappa V. This is something that we have seen in chapter 1, and so you can go and you can simplify it. And if you do the simplification similar to what we have done using the ideal gas equation of state, you can actually see that the speed of sound for liquids and solids as well is simply given by 1 over kappa times the density of that liquid or solid. And because kappa is a very small number, oftentimes in the order of 10 to the minus 7, 10 to the minus 6, and 10 to the minus 8, and so forth, and it's a very small number, and it's in the denominator, you can see that it's going to be an extremely small number. And so when you take 1 over an extremely small number, and you're going to get a very, very large number, and you take the square root of that number, that would give you the speed of sound in solids and liquids. And so because of this reason, that the speed of sound in condensed phases, which is to say liquids and solids, is generally much higher than gases. So these are the concepts, and so the Joule-Thomson coefficient and the speed of sound equations are absolutely essential equations. I have had questions in midterms based on these two concepts almost for the last 10 years, every single year, and so I just want to make sure that you are comfortable, as we work some examples, and the TS also will hopefully bring some examples during the course of the week. Thank you very much, and I will stop in here.